So we're continuing on working with one-sided limits. So I kind of just want to review the one-sided limits, and then we're going to look at some examples that will hopefully help you understand and be able to do your homework. So the following we have here, given a function f of x, if we're looking at the limit as x is approaching a of f of x, so that has that little plus subscript in there, or not subscript, superscript, is equal to the limit as x is approaching a on the left, with that little negative superscript of f of x equals L. So if that is the case, then the normal limit will exist. And we can say that the limit as x approaches f of x, or sorry, the limit as x approaches a of f of x is equal to L. So left-hand side limit equals our right-hand side limit. That's L, then the limit exists, and that is also L. We can go in the reverse direction though. So likewise, so this is like an if and only if statement. We can go either direction and it works. So if we know that the limit as x approaches a of f of x is equal to L, then we know that the limit as we're coming in on the left and the right, we're also getting back L. I guess we should put in the stipulation as long as that's in the domain. Because we had seen yesterday where our bounds, our domain was bound. And so we would have a left-hand bound or a right-hand bound limit, but not both. So let's look at a couple of examples where we're going to look at algebraically solving this as we're approaching either the left or the right-hand side. Yesterday, we looked more at looking at these when we were dealing with piecewise functions, but we're not always dealing with piecewise functions. So let's look at something that is an example of not a piecewise function, but looking at a limit, one-sided limit. Okay, so we have an example now in front of us. The limit as x is approaching negative 0.2 from the left of the function square root underneath the radical, the radicand, is a fraction, and our numerator is x plus 11, and the denominator is x plus 2. First thing we need to worry about is that what we're approaching, that negative 0.2 on the left, is that part of our domain. And so kind of looking back at algebra, recall, well, in order to be part of our domain, when we plug in a number, we need to get back a real number. And since we have a radical and we have a fraction with a variable in the denominator, we have to worry about a couple of different things. And so let's look at our domain. Well, we know that what's underneath the radical, which is x plus 11 all over x plus 2, in order for us to get back a real number, this has to be greater than or equal to 0. How we solve rational inequalities is different than what we solved when we were solving linear inequalities. This is where we looked at our critical numbers, and those were values. Once we got our rational piece to one side and it was greater than, or whatever the inequality was, to 0, we looked at our critical numbers, and our critical numbers were the things that set the numerator equal to 0. So that would be x equals negative 11, because that sets my numerator equal to 0, and values which set my denominator equals 0. So x, it really can't be, but x equals negative 2, because we can't divide by 0. And so recall, I don't know if you guys remember, just kind of really quickly going through. This is where we placed our critical numbers on the number line, and we started testing values to see if we got back a true or a false statement. And so we could choose a value to the left of negative 12. So let's say, how about x equals, a value on the left of x equals negative 11, and I want to use negative 12. And we want to know if we plug in negative 12 wherever we see an x, would this be a true or a false statement? I'm really just curious if it's true or false. I don't really care what value I get back. So let's just think about the numerator. I plug in -12 plus 11. That would give me back a negative number in my numerator, all over -11 plus 2. So that gives me a negative number in my denominator. Is that a true statement that that's greater than or equal to 0? Yeah, negative divided by a negative, right? It's a positive number. So a positive number is greater than or equal to 0. So this is true. So I'm going to just put a T up here. So that means any number that we would have chosen to the left of -11 should have worked if we plugged it in there. So now choose something that falls between x equals -11 and -2. So let's say we chose -3. And we go back in and we plug it in wherever we see an x in that inequality. We want to see if it's true or false. So -3 plus 11, that gives me 8. That's a positive number. And -3 plus 2, that gives me -1, so a negative number. Is that greater than or equal to 0? No, because if we take a negative divided or a positive divided by a negative, it's a negative. So this is false. So any number you would have chosen in between -11 and -2 should have came back as a false statement. And one more, choose something bigger than our other critical number, last one, -2. So if we plugged in, let's say x equals 0 is always a good one if it falls in one of the intervals. So if we plug in 0 into the numerator, we get back 11, which is positive, all over 0 plus 2, which is 2, which is positive. And is a positive over positive greater than or equal to 0? And it is. So this is true. Okay. A long kind of way to show, first of all, that -0.2 is in our domain. If you look at this, our domain, we know are all values coming in from -infinity till we hit -11, and it's okay to hit -11 because that makes it equal 0. So I'm going to have a bracket. So -infinity to -11 union. I'm not including -2 because x can't be -2. That's what sets my denominator equal to 0, and it's not part of my domain. And so I have parentheses -2 to infinity. And so basically -0.2 is not one of those endpoints of my domain or in values of my domain. So I'm not too worried that this is going to be jumping or anything. We can use our rules of exponents, right? For limits or our rules of limits to rewrite this. So technically we can break this down. We took the radical or and put it outside of our limit. And so now we're taking the limit of that rational function. Another rule, and normally I wouldn't do this, I would just do direct substitution, said that I could take the limit of my numerator. So limit as x approaches 0, -0.2 of my numerator, x plus 11, all over the limit of my denominator as we approach -0.2 of x plus 2. So let's just go in and do direct substitution. So if we do direct substitution wherever we see an x, and then simplify. So doing that, we have the square root of -0.2 plus 11 all over negative 0.02 plus 2. Okay, so 11 plus negative 0.2, I'm really subtracting, right? And so that's going to give me 10.8. 2 minus 0.2, point in there. That's going to give me 1.8. Seeing if I can do this without a calculator, but technically we can get rid of our fractions or our decimals within our fractions, right? By multiplying by a fancy 1. I need that decimal place to move over once. So I can multiply both the numerator and denominator by 10 underneath that radical. So I have 108 over 18. So they're both at least divisible by 2. 2 goes in, and I can break it down as 2 different square roots if I want, but I guess I can wait. So 2 goes into 108 54 times. 2 goes into 18 9 times. So it actually goes in there evenly, right? Because 9 times 6 is 54. And so this will be equal to the square root of 6. Okay, so if we looked at the graph of that, what that would be showing us is x is approaching negative 0.2 on the left, and it's even the same thing on the right. We would get back square root of 6. Okay, so just a real quick, great question about, why couldn't we just gone through and just did our direct substitution? Why did we have to go through that piece of finding the domain? And technically, we really don't have to, but if we're looking at a limit, that value that we're approaching x has to be in the domain. So we did a lot of extra work that we really probably necessarily didn't have to. And if it wasn't in the domain, we would have seen that we would have had a trouble spot when we plugged in that number. And actually, if it wasn't in, it might have been, yeah, I don't know what I was going to say. So basically, just being able to do direct substitution in this case would have been okay. Okay, so for in this example, it asks us to find the limit as x approaches c from the left, from the right of f of x. And it tells us that our function f of x is x plus 15 times the rational function or rational piece, which is absolute value of x plus 10. And then that's all over x plus 10. And we're looking at the value that we're approaching from the left to the right to be negative 10. So right away, I notice right here that negative 10 is not part of our domain, right? Because if I plug in negative 10, wherever I see an x, I'm going to have that denominator equal 0. So notice, but that doesn't mean that the limit doesn't exist. And we've seen that before where what might have not been defined at the value we approached our limit or might not have even been defined. But so notice that x cannot equal negative 10. X equals negative 10 is not part of the domain. The other thing that you need to notice is that we have an absolute value function in there. An absolute value function is written or can be written as a piecewise function. Okay, so note. So recall the absolute value function is the distance between the number and 0 on the number line. It's always a positive number. And so one way to write the absolute value, it depends on the value you're plugging in for x. So if you plug in a positive number in for x, so if you let x be greater than or equal to 0, when it spits out the answer, right, it's going to be the same number you plugged in. So the absolute value of 1 is just 1. The absolute value of 1.5 is just 1.5. So the answer that we get back is just x. But if you go in and you plug in a negative number wherever you see an x and the absolute value of x, well, when you get the answer back, you're taking the negative of what you had plugged in. So if I took the absolute value of -1, my result is the negative of a -1, which is +1. So my result in this case is -x. And so we're actually going to want to break down the absolute value that we're dealing with in here, x plus 10. So we know, what do we know about this? The absolute value of x plus 10. So if we plug in a number that is bigger than -10 or equal to, so let's say x is greater than or equal to -10. Well, if I do that, like if I plug in -10, I get the absolute value of 0. If I plug in -11, I'm sorry, bigger than. So if I plug in -9, so I would get back -9 plus 10, which is 1. And so if I'm plugging in this value, I'm going to get back this result, x plus 10. That makes sense. So if I plug in, though, a number that is less than or equal to -10, or sorry, just less than -10, not equal to. So for instance, -11, that's less than -10. If I plug it in here, that would give me absolute value of -11 plus 10. That's going to be just absolute value of -1, which is 1. And so technically what we're doing is we're taking the negative of x plus 10 or -x minus 10. Okay, so those are our two equations for just the absolute value. And then again, we're looking at the limit. As x is approaching -10 on the left-hand side of this whole function. And we can break this whole function down again, and that could be helpful for us when we're looking at this and taking the limit. So remember, if we were looking at the limit as x approaches a number of a product of two different functions, we could break it down as the limit of the first times the limit of the second. And we were looking at the limit of a rational function, we could look at the limit of the numerator with the limit of the denominator. So I'm going to just rewrite this using our limit rules. So taking the limit of our first piece, I'm going to call it x plus 15, all times the limit of x approaches -10 on the left of the absolute value of x plus 10, all over the limit as x approaches -10 on the left of x plus 10. Okay. If we plug in -10 on the left and -10 on the right, I would get the same thing if I plugged it back into that piece of just x plus 15. And so this piece of my limit, I can just do direct substitution, and I get negative 10 plus 15, which is 5. So that limit I know is 5. Now we have this times, and this is where we gotta be a little more careful. If we look at the limit as x is approaching negative 10 on the left, so that's telling me right here that my values I'm plugging in they're going to be smaller than negative 10. And so that tells me that I would be plugging it into this piece of my absolute value. And let's just think about it. So if we plugged in a number, doesn't really matter, but if we plug in a number into that absolute value, our number that we're going to get back is positive, isn't it? Let's just put positive right there. Same kind of idea though, if we're looking at the limit as x is approaching negative 10 on the left, this number is actually going to be smaller than negative 10. And when we're looking at negative 10.1 plus 10, that's going to be a negative number. Actually, I think what I want to do, let's do this instead. Sorry. I think what I want to do instead is let's break this down. I'm going to write this as the limit. And I'm just going to write it as one limit as negative 10 approaches the left. We said that again, we are going to use the piece where it's less than negative 10, which means I'm going to use this equation. So I'm going to use this negative x minus 10 all over the other piece, which is x plus 10. Those are almost identical. And if I went in and I plugged in negative 10 right now, and for that limit, I would get that 0 over 0, that indeterminate form, which we don't like. And so I noticed one of the ways to deal with that was to do factoring and canceling like factors. And so notice that I can pull out, I'm going to bring down my 5 from that first limit. For my numerator, I can pull out a negative 1. So if I pull out a negative 1 from my numerator, I'd be left with x plus 10 all over my denominator of x plus 10. So we can now cancel like factors. And recall, if we look at the limit of a constant, which we're left with, which is the limit of the function negative 1, the limit of a constant was just that constant itself. So this would just be negative times negative 1. So 5 times negative 1 gives us what that limit would be if we were approaching it from the left, which would give us negative 5. So almost the exact type of reasoning for when we're coming in on the right-hand side, and I'm just going to put it up here. So limit as x is approaching 10, negative 10 on the left equals negative 5. So now we want to do kind of the same idea, but now we're wanting to look at what is the limit as we're approaching negative 1, not negative 1, negative 10 on the right-hand side. So same sort of idea. I can break this down, x plus 15 all times the absolute value of x plus 10 all over x plus 10. And so now when we're plugging in numbers, our numbers are to the right of negative 10. So this is x is greater than negative 10. So if x is greater than negative 10, that tells me that I need to use this equation for my numerator. So we can break it down, limit x approaches negative 10 on the right of the first piece, x plus 15, times the numerator, which we're going to rewrite using x plus 10, all over our denominator of x plus 10. So if we plug in direct substitution, we get a 0 over 0, but notice those are the same thing, x plus 10 divided by x plus 10. And so technically those cancel, just leaving us with a 1. And so now when we look at the limit as x is approaching negative 10, plugging in negative 10 wherever we see an x, we get negative 10 plus 15. All times 1. So this is 5 times 1, which is 5. So the limit on the left is going to negative 5, where the limit on the right, as we approach negative 10, was going to positive 5. That one was a little more, I think, complicated than the first one. So you might have seen before what is called the greatest integer function. And what the greatest integer function is a function that gives us the greatest integer less than or equal to the number. So the greatest integer less than or equal to a number x is represented by, I've seen it as with like kind of brackets around the x. I don't know if what's showing us right now is because of the text. And we round off the given number to the nearest integer that is less than or equal to the number itself. So technically, if we kind of start thinking about this, any number you plug in that is an integer is going to give us back the integer. But if it's a fraction, so let's say we had 0.5, this direction tells me that I'm going to look at the integer. So an integer that surrounds 0.5 is either going to be 0 or 1, but it tells me to look at the greatest integer less than or equal to the number x represented. So the integer that is less than but nearest to 0.5 is 0. So at 0.5, I know I have a point of 0. If I plugged in any number between 0 and 1, I'd get back 0. So if I plugged in 0.99, that's not an integer, but the biggest integer to the left is 0. So I have what is called this step. It's going to start looking like a step. And at 0, I also get back 0 because that's an integer, so it's closed. I can get really, really close to 1 on the left, but it's an open circle there when I'm coming in the left right here at 1, 0. Because technically, when x is 1, that's an integer, I get back itself 1. So at 1, 1, I have a closed circle. Any number number you choose in between 1 and 2, so like 1.5, well, that's not an integer, but the integer that's biggest to the left of 1.5 would be 1. So I'm going to have this horizontal line again with a solid circle at 1, 1, and then I'm going to have an open circle at 2, 1. Because once I hit 2, that's an integer, and it's going to be a closed circle at 2, 2. So this is where it's kind of called the step function. It keeps on going like a step. Okay, so that is going to be helpful for us when we look at our next example to remember what that step function looks like and what it's telling us. Okay, so our next example wants us to find the left and the right-hand limit of the following. So we're looking at the limit as x is approaching -1 from the right of the step function x all over just x itself. And we want to look at the limit as x is approaching -1 on the left of the same function, step function of x divided by x. Okay, well, let's go back and kind of think about this. If you're plugging in a number and we're coming in on the right of x equals -1, this means I'm choosing numbers of x which are greater than -1, but close. So let's think about that. So if I plugged in, let's say, -0.9. -0.9 is close to -1 and it's on the right. But if I plug that value into the step function, that actually is not an integer, right? So -0.9, the integer to the left of -1 is -1. Sorry, the integer to the left of -0.9 is -1 all over. And so if I'm plugging in numbers close to -1, it's going to give me this x value, which is negative. Well, it's not really -1, it's x. Let's pause. Okay, so again, that step function, as we're getting closer and closer to -1 on the right-hand side, it's going to give us the greatest integer to the left of that, which is -1. Think of this as, because it's defined, that we're using this direct substitution. And so for the denominator, because I can do direct substitution, I can look at the limit of the numerator over the limit of the denominator. And if I plug in -1 in for x here, this is all over -1. And so my result that I get back is +1. Okay, so that is if I'm coming in on the right-hand side. If I'm coming in on the left-hand side of -1, I'm coming in here on the left-hand side, I know then that my values of x are going to be less than -1, but close. The problem is when I'm plugging that into my numerator and I look at the greatest integer that is less than that -1.1 or -1.2 or -1.001, that greatest integer that I'm going to get back would be -2. So if I do direct substitution, I would get -2 back from my numerator. Plugging in -1 on the denominator, I get -1. And so this would equal 2. So our limit on the left and the right are different than one another. I'm just going to plug it in really quickly. So limit exists and it's equal to 2. And then if you want, we can look at the graph, but we're pretty much out of time. Okay, so that is the end of this lecture. We'll continue with these one-sided limits tomorrow and look at a property that we looked at last week using the sandwich theorem, that the limit as x approaches 0 of sine x over x is 1. And being able to manipulate these limits, these functions to look like that so we could use that fact. So let's stop there for the day.